Now I will be discussing the two-phase method for solving linear programming problem. For this, taken problem, maximization of z is equal to 5x1 minus 4x2 plus 3x3 subject to the constraint, say constants. First, 2x1 plus x2 minus 6x3 is equal to 20. The second, 6x1 plus 5x2 plus 10x3, which is less than equal to 76. 8x1 minus 3x2 plus 6x3, which is less than equal to 50. Here, one of the constants is of equal to 10. For solving, first we have write the problem in its standard form. So 2x1 plus x2 minus 6x3, as it is equal to types, we have write as it is same, but in the second constant 6x1 plus 5x2 plus 10x3, here less than equal to type. So if we add s1, inequality become equation, and 8x1 minus 3x2 plus 6x3, again introducing another slack variable s2, now it is 50. Here all the x1, x2, x3 are non-negative. To form in the standard form, we introducing s1 and s2 as it is all of non-negative. Now if we start the basic variable s1 and s2, if we take s1 s2 as a basic variable, means if we put x1 equal to 0, x2 equal to 0, we find s1 equal to 76, s2 equal to 50. And if we take these two variables in our simplex table, means if we take s1 s2 as a basic variable, we cannot find a identity matrix of 3 cross 3 type, because in the first equation we do not have any slack variable, so thus we cannot perform simplex method. We cannot perform simplex method as by taking only s1 and s2 as a basic variable. Thus, what we have to do? If we add an additional constants, we have to make an identity matrix in the first iteration. So we have to have any additional variable have to add and make an identity matrix. Thus, the following constants 2x1 plus x2 minus 6x3, if we add an additional constants a1 here, and the second constants are written as same, $50. Now the problem, we are introducing two-phase method. In case of two-phase method, the maximization problem, first we solve by taking maximization function by taking only artificial variable. In case of maximization, we have to take the minus, subject to the following constants. Now we will make an simplex table, and our coefficients are the variable x1, x2 and x3. So the x1, x2, x3 are the decision variables, and our artificial variable is a1 and slack variable s1 and s2. We are only solve maximization z equal to -1 subject to the following constants. So the objective function, the coefficient of x1 is 0 here, coefficient of x2 is 0, x3 is 0, the coefficient of a1 is -1 and coefficient of s1 and s2 are 0. Now we take a1, s1 and s2 are the basic variables, and the coefficient of a1 in the objective function -1, s1 0 and s2 0, the coefficients of a1, s1, s2, and here now all the constants put in the table. So here the 2x1 plus x2 plus 1x2 minus 6x3, the coefficient of a1 1, it is 0 0. The second equation 6x1 5x2 10x3, there is no a1 here, and the coefficient of s1 1 and 0. In the second it is written. In the third equation 8x1 minus 3x2 6x3 0 a1 0 s1 and 1 s2. And the solution, when write the solution on the right hand side, is 20, 76 and 50. So in case of two phase method, first we solve maximization z equal to -a1. Here now we have to find zc. Our aim is to remove a1 from the basic variables. Zc is the coefficient of and dot product of column of x1. So -1 into 2, it's a -2, and +0 plus 0, it's a -2. -1 into 1 plus 0 into 5 plus 0 into -3, it gives -1. Similarly, the dot product between the coefficient of basic variable and the column of x3, it gives 6, -1, 0 and 0. As artificial variable is present in the table, so we have not find the solution. Now the optimality criteria to find Cj minus Zj. Cj is coefficient of objective function and Zj we already write here. So 0 minus of -2, that is 2, 0 minus of -1, that is 1, 0 minus 6, -1 plus 1, that is 0, 0 and 0. the positive values 2 and 1 are present in the Cj minus Zj row. So we choose the maximum among 2 and 1. So here 2 is maximum, means x1 will enter in the basis, but which variable are leave? Thus x1 enters, which variable are leave? We find ratio of the entering variable from the solution. So 20 by 2, it's a 10, 76 by 6 and 50 by 8. And choose the minimum among them. Here all the are positive, so choose the minimum. Here it is 10, it is 6 point something, so it is minimum, then the corresponding value is 8. So x1 will enter and leave s2 from the basis. Here this is called pivot column, means in the next step we have to make this is equal to 1 and corresponding values of columns are 0 and 0. By Gauss elimination method we can solve. So take further, now s2 will leave and x1 will enter. So the basic variable are still a1, s1, but in place of s2 there is x1, and the coefficient of a1 from the in the objective function is -1, 0, and the x1 is also 0. Here for making 8 to 1 we have divided this row by 8 simply. So 8 by 8 equal to 1, minus 3 by 8, 6 by 8, it is 2 by 4, 6 by 8 means 3 by 4, 0 by 8, that's 0, 0 by 8, 0, and 1 by 8. Here again 50 by 8. The first goal is complete, as now replacing 8 becomes 1 by dividing this row by 8. Now we have to make this column to 0. So by reducing, what we have to write, there's a vector 2, 1, minus 6, 1, 0, 0 and 20. Minus, if we subtract this, 1 minus 3 by 8, 3 by 4, 0, 0, 1 by 8 and 50 by 8. If we have to make 0 here, that we have to multiply by this row by twice time and subtract it. So this row minus twice time of this row will give 0 here. Similarly for other values, here 2 minus 2, that's 0, it's our aim, here 0. 1 minus, so plus 6 by 8 or 9 by 8 means here 14 by 8 means 15 by 4. Again minus 6 and minus 6 by 4, it will give minus 15 by 2. Similarly, 1 minus 0 will give 1, 0 minus 0 will give 0, 0 minus twice time 1 by 8, it means it's a minus 1 by 4, and 20 minus 100 by 8, that give 60 by 8, means 30 by 4, or you can say 15 by 2. So we can write here 0, this rows minus twice time of this rows. 0, 15 by 4 minus 15 by 2, 1, 0 minus 1 by 4, and here 15 by 2. Again, we have to check 2 minus 2, 0, 1 minus of minus plus 6 by 8, it's 14 by 8, means it is 7 by 4. Here it is 7 by 4. Again, minus 6 minus twice time 3 by 4, it gives minus 15 by 2. Similarly, 1 minus 0, 1, 0, and last column for the solution, 20 minus twice time of 50 by 8, it gives 15 by 2. Similarly, for getting this row, we have to make here 0. For making 0 here, what is the vectors are 8, minus 3, 6, 0, 0, 1, and 50. Sorry, you have to estimate this row here. Therefore 6, 5, 10, 0, 1, 0, 76 minus 1 minus 3 by 8, 3 by 4, 0, 0, 1 by 8, and 50 by 8. For getting 0 here, we have to subtract by 6 times of this row, means this row minus 6 times of this row, we make 0 here. And similarly for the other values, so here 6 minus 6, 0, again 5 plus 18 by 8 give 40 plus 18 by 8 gives 29 by 4. It's a calculation. Again 10 minus 18 by 4. Here 10 minus 18 by 4 give 40 minus 18. By 2. And similarly 0 minus 0, here 0, 1 minus 6 times is again 1, 0 minus 6 by 8, minus 3 by 4 and 76 minus 6 into 50 by 8. It will give ultimately it gives 77 by 2. The here 0, 29 by 4, 11 by 2, 0, 1, minus 3 by 4 and 77 by 2. Again, artificial variable is still present. We have to go further. For further, we have to calculate Zj. The rough part I will move. The rough part I will erase. For Zj, for computing Zj, so minus 1 into 0, 0 plus 0 into 0 plus 0 into 1, it will give 0. Minus 1 into 7 by 4 will give 7 by 4. It will give 15 by 2. Minus 1 into 1, minus 1. 0. 1 by 4 minus, as artificial variable is still in the table, we do not have to write z. Here, for the optimal criteria, we have to calculate Cj minus Zj. For Cj minus Zj, the coefficient of x1 is 0, 0 minus 0, 0, 0 minus 7 by 4, so minus 7 by 4, 0 minus 15 by 2, minus 15 by 2, minus 1 plus 1, 0, 0 minus 0, 0, 0 minus 1 by 4. Here, Cj minus Zj is there. We again calculate 0 minus 0, 0, 0, 0, 0, 0, minus 1 into 7 by 4, it will give minus 7 by 4, minus 1 into plus 15 by 2, minus 1, 0, 1 by 4. Here Cj minus Zj, it will give plus 7 by 4, minus 15, 0 minus 15 by 2, minus 15 by 2, minus 1, minus minus of 1, 0. Now here only positive value is 7 by 4, means x2 will enter in the basis and which variable will leave, it depends upon the ratio. So the ratio of entering variable from the solution. So 15 by 2 divided by 7 by 4, as it is negative sign, we did not calculate the ratio here, as it is of negative type. 15 by 2 divided by 7 by 4 and 77 by 2 divided by 29 by 4. So the minimum value will give here 15 by 2 into 4 by 7 and here 77 by 2 into 4 by 29. So minimum value will occur if we calculate the minimum values is here. Thus entering variable is x2 will enter and a1 leave from the basis. Thus the again we go further. Now in place of a1 we have to write x2, and s1 and x1 is same. Now this is our pivot column. We have to here make 1 and 0 0 here. For doing this, we divide by this row by 7 by 4. It will give 0 1 and minus 15 by 2 divide by 7 by 4. Will give minus 30 by 7, and 1 divided by 7 by 4 will give 4 by 7. 0 divided by anything is 0. Minus 1 by 4 divided by 7 by 4 it will give minus 1 by 7, and 15 by 2 and 15 by 2 divide by 7 by 4, 30 by 7. Now this is our pivot column. We have to make 0 here and 0 here. For doing this, say it is our S2, then S2, if we subtract S2 by minus 29 by 4 times new X2. If we do this, it will give S2, sorry, here S1. So 0 minus 0, 29 by 4 minus 29 by 4, it will give 0. Our aim is solved. Similarly, for other, we have to simplify 11 by 2 minus plus 29 by 4 into 30 by 7. If we solve, it will give 256 by 7. Here artificial variables are removed. We don't have to estimate the artificial variable as it is removed from the simplex table. Similarly, it will give 1, 2 by 7 and 52 by 7 by applying these row operations. Similarly, for x1, if we change x1, we have to make here 0. So x1 changing to by here new x2. If we multiply or add 3 by 8 times of new x2. It will give 1 plus 3 by 8 times of 0. This will 1. Similarly, it will give 0 here and minus 6 by 7. Need not estimate artificial variable here, and 0 by doing this 1 by 4, and getting here the value, it will be x1. Here x1 is 50 by 8 plus 3 by 8 times new x2, it have 30 by 7. It will give will give simply 55 by 7, as 50 by 8 plus 3 by 8 times new x2, here new x2 is 30 by 7, and if we simplify, it will give 55 by 7. Now we have checked the optimal criteria. For this we have to find Zj. Here the basic variables are x2, s1, x1, and the maximization z is equal to minus 1. So the coefficient of x2 is here 0, 0 and 0. So for Zj we have to estimate 0 into 0 plus 0 into 0 plus 0 into 1, it will give 0. Similarly 0, 0, and as artificial variable, not in the simplest, we did not find the value of artificial variable. Here again with 0, 0, and the Zj is 0. To check the optimality criteria, we have to Cj minus Zj, and Cj minus Zj is 0, 0, 0 and 0, 0. Now this is the optimal table for the problem maximization z equal to minus 1, as there is no positive value in Cj minus Zj row, as all our Cj minus Zj are satisfy the following criteria for the optimality. But our problem is to maximization z equal to 5x1 minus 4x2 plus 3x3 subject to the constants. It is the problem is maximization z equal to minus 1, means if we remove the artificial variable from the table and we reach the optimal table, now we have, this is first phase of the problem. So in the two-phase method, the first phase is finished as we have removed the artificial variable from the basic variable. And if you look, x2 equal to 30 by 7, x1 equal to 50 by 7, but the cost function is 0 for the maximization z equal to minus 1 the problem. Now this is phase 1. Now the phase 2, for the phase 2 we have our objective function, as we remove the artificial variable. Now our objective function is the same as our take the original problem, and the table x1, x2, x3, only we have to take the slack variable by removing artificial variable, and just as it is maximization z is equal to 5x1 minus 4x2 plus 3x3, so the coefficient of x1 is 5, x2 is minus 4, and x3 is 3, plus 0s1 plus 0s2. So here 0, here 0. Now, which are basic variable? The optimal table of the phase 1 are the basic variable, and we can take the basic variable from the optimal value of the phase 1. So x2, s1, x1 are the basic variable for maximizing this problem in phase 2 method. So, and now the x2 coefficient is -4, s1 is 0, and x1 is 5. And just copies all the values from the optimal table to the phase 2 values. So here it's a 0, 1, -30/7, as it is an artificial variable. There is no artificial variable here, and now the coefficient of s1 is 0 and -1/7, and the solution 30/7. You can say it is solution, and the coefficient of s1 is 0, 0, 256/7. The coefficient of s1 is 1 and 2/7, 52/7, and for x1 is 1, 0, -6/7. The coefficient of s1 is 0, and s2 is 1/4, and here it is 55/7. Now we find Zj. For Z1, the dot product of coefficient of basic variable into corresponding column. So -4 into 0 plus 0 into 0 plus 5 into 1, it will give 5. -4 plus 0 plus 0, it will give -4. And -4 into -30/7 plus 0 plus -5 into 6/7. If we solve, we got 90/7. That is 120/7 minus 30/7, 90/7. Similarly, -4 into 0 plus 0 into 1, and it will give 0, and -4 into -1/7, it will be 4/7, plus 0 plus here 1/14 will be here. So here plus 5/14, and if we solve, it will give -4/7, so 4/7 will give 13/4. And similarly, -4 into 30/7 plus 0 into 52/7 plus 5 into 55/7, it will give 155/7. This is our Zj. Here it will 8 plus 5, it's 13/14. Now what is our Cj minus Zj? So Cj minus Zj is 5 minus 5 is 0, minus 4 minus of minus 4 will 0, 3 minus 90/7, 3 minus 90/7 have will 69/7 of negative sign, minus 69/7, 0 minus 0 0, 0 minus 13/4 will be minus 13/14, and again now we look, this is optimal table for phase 2 or not. Here all the Cj minus Zj are either less than equal to 0 or equal to 0, means there is no positive value value, it means this is our optimal table for phase 2, and the solution of the given problem is x2 equal to 30/7 and x1 equal to 55/7 and the z which is 150/5/7. So this is our solution to the given problem by using two-phase method. So in two-phase method, first we have phase 1 and second phase 2. In phase 1 we have to obtain maximum z equal to -1, as there is only artificial variable added in the first, so only one artificial variable, so we have right maximization z equal to -a1, means all the coefficient of x1, x2, x3 and s1, s2 are 0, and we make a simplex table for all the constants and the objective function. And now our aim is to remove artificial variable from the simplex. Now in the final optimal table, here there is no artificial variable in the basic variable, so and all the cj minus zj are less than equal to 0 type, so the phase 1 is finished when we reach the optimum table. Now in phase 2 we take our original problem, as our original problem is 5x1 minus 4x2 plus 3x3 and all the select variable 0s1 plus 0s2, and taking all the values from the optimal table from the phase 1. So the basic variable for phase 1 x2 s1 x1, so here x2 s1 x1, but we are maximizing our original problem here, so the coefficient of x2 is -4, s1 is 0 and x1 is 5, and the objective function is 5 -4 3 0 and 0, and we take all the values from the optimal table for phase 1 as it is. Now we have estimate for taking optimality criteria, we estimate zj and cj minus zj. Here all the cj minus zj are less than equal to 0 type, means this is optimal table in phase 2 for this maximization problem. Thus the solution here x1 and x2 and the maximization z is equal to 155/7. So this approach is known as two-phase method.